Okay, here we are doing the free response questions in about 7 minutes. This would normally take you about an hour to do, so I'm going to talk pretty fast. We're adding vectors, okay, and the vectors, if they're given to you in polar form, which you're told, then you want to give the answer back in polar form. So what we have to do is translate these into rectangular form. The only way you can add vectors is if they're broken down into their x and y components. So we have this little formula. Our cosine theta gives me the x value of the vector, and our sine of theta gives me the y value. So I've applied that. 7 cosine of 107 right there, it's -2. 7 times the sine of 107 gives me this. First I sketch them. So if I'm at an angle of 107 degrees, I'm rotating around 107 degrees, a little bit past 90 degrees, and I've just made some length for me be 7. Well, 6 is a little bit less than that. In this angle, 215 degrees, that was 215 on your practice test. That is just a little bit past 180, so I'm over here. When you add this vector to that vector, you're going to go down the middle. You use the parallelogram method. You sketch a line parallel to this one, and then you sketch a line here parallel to this one, and then the resultant goes from the origin to where those two parallel lines intersect. Okay, don't do anything diagonal across there. That's crazy. The approximate length looks like to me it's going to be longer than 6. When we break it down into the x and y components, we add the x's, so -2 plus a -4, and then we add the y's, +6 plus a -3. I get -6.9 and +3.2. When I convert back to polar, I square each of those numbers, and then I add them up and square rooterize it. That is it right there, and it gives me 7.6. So that is longer than those individual vectors. Then find the magnitude in the direction of, find the angle. That's the angle of rotation, so it looks like it's going to rotate around almost, I don't know, maybe 180 degrees, but not quite. So what I do then is I use my formula for the reference angle, it's called alpha. It's the inverse tangent of the y value over the x value. Drop off the negative signs. It's just positive because we're really just making a triangle here. And triangles, for that angle, we're talking about positive lengths. And when I get that angle alpha, I then take it away from 180. Each quadrant has its own rule. In quadrant 1, the rule is that the alpha reference angle is the same as theta. But here, when I find this angle, I have to take it away from 180 to find the angle of rotation theta. So there it is, 154.96 degrees. Try to go to 3 decimal places. I was running off the edge of the paper, so I chopped one off. So here's a separate problem, a different problem. At 8 a.m. one morning, one ship sails, another ship sails, and we're trying to figure out how far it is between the two ships. So draw it carefully. From 8 a.m. till noon, somewhere here, at noon, how far are they apart? Oh, sorry, at 1 p.m., I lied. That's 5 hours later. So 5 hours times 50 miles an hour is 250 miles. So when you say 190, and this way is north, you rotate past south, that's 180 by 10 degrees. So I can just label that as being 10 degrees. When I go at a bearing of 165, that's 15 degrees short of straight south. So there's my 15 degrees. So I have a triangle here that's like side angle side, where that's known to be 250, that's known to be 200, and that's 25 degrees. So I just do law of cosines again, like we did in the other problem, and I get 108.9 miles. Okay, that's problem 1. Problem 2, we've got like a combo here where there's a top pattern and there's a bottom pattern, and the top one is arithmetic, the bottom one is geometric. So you just are going to come up with 2 separate formulas. Here we just can keep whatever that pattern is. It's going up by 3, up by 3, up by 3, and it's doubling, 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 so that's pretty easy. To find the patterns, just do the arithmetic pattern, which is the first term, 5, plus the common difference, which is 3, always n-1. The bottom pattern, the bottom formula, is the first number 3 times the magic multiplier, that common ratio it's called. 6 over 3 is 2, 12 over 6 is 2. It's 2, then it's raised to the exponent n-1. and just leave it at that. You can't simplify it. You can't do anything else. Determine a sub 12, the 12th term. When I plug in 12, both top and bottom, I get 38 over 6,144. Does the sequence have a limit? Heck yes, it does. That bottom is getting really big really fast. That is going to get closer and closer and closer to 0. It's almost like Bobo, where bigger on the bottom, the number that's bigger on the bottom, means that the limit goes to 0. What would the sum of the first 100 numerators, read carefully, not terms, but numerators, be? Well, you just plug it into our summation formula, and we get 1,503,500. That's going to be the first term plus the 1,000th term, and times 500. That's one of your formulas. What would be the sum of the first 50 denominators? Oh yeah, I wrote the formula. There's the formula right here. First term, last term, or the 1,000th term, that should have an extra 0, and 1,000 over 2. This is the formula for the first 50 denominators. It's going to be the first term 3, 1 minus r to the 50th, all over 1 minus r, in which case it's 2. You get a huge number, 3.3777 times 10 to the 15th. If you move all those zeros over, it's roughly 3,000 trillion, or a little bit more. Scientific notation is great on that one. Number 3 is, given the polynomial, f of x equals, well, this is a polynomial, we're told that. I want to put it into standard form. That's by degree, first degree, highest degree, then next, and then the constant term. So there it is in standard form. The lead coefficient is 2, the degree is 3. Sketch a graph, type that into your calculator, get the window correct. Make sure you label the window a little bit better than I did. What's the end behavior? Well, the left hand is down and the right hand is up. You can just write that out in a sentence. What are the exact coordinates for the y-intercepts? The y-intercept is when x is 0, so that's negative 50. The exact coordinates for the x-intercepts, this is the tough one. You want to know where are these exact values. If you put them on your calculator and go in and find the zeros, you'll see that one is decimal, another is decimal, and the third one is the constant term, negative 2. So this, I think, let's see, I think this one's a negative 2. So what do? I have to divide out that factor. If the factor, if the 0 is at negative 2, then it's the opposite. It's x plus 2 that'll be the factor. Polynomial long division. I go carefully here where I look at 2x squared is what it takes to multiply by x to give me 2x to the third. I have to multiply this times both of these guys, and I get 2x to the third plus 4x squared. And then I just subtract very carefully. I change the signs and add, and I get x squared. I bring down the negative 23, and I repeat. And when I divide this out, you get 2x squared plus x minus 25. This will not factor. There's no numbers that multiply to make 25 that then cancel and give me 1. So I put it into the quadratic formula. You'll have a lot more room to work than I did. I squeezed it in here, and I get the decimals that match. Oh, it looks like this was the negative 2. So this is the 0 on your calculator. The other ones are about plus and minus 3, and but it's the exact values I want, just like that. So make sure that's clear. All right, on to 4. Similar but different. It's a rational function. So it's all about finding the zeros and knowing what goes on down in the denominator to give me vertical asymptotes. I can just graph this lower polynomial, and that will show me that it crosses at 5. I can factor that out, again with polynomial long division, and I will get x squared plus 1 as the resultant when I factor that out. The top, I have to try to factor that as well, and I get x minus 5 and x minus 1. The x minus 5's cancel. So really, this is what the graph is going to look like if I graph that in alone. You get this weird squiggly thing. There are no vertical asymptotes because there's no way that x squared plus 1 will ever equal 0. If you're not sure, just graph that denominator on on your calculator, and you'll see that it is like a parabola that is above the x-axis, okay? When I graph it as a rational function, it looks like this. I can take and go back to my original factors that I canceled out, and that'll tell me where the hole is. It's when x is 5. So if I plug in 5 up here, 5 minus 1 is 4. If I plug in 5 here, 25 plus 1 is 26. I can simplify 4 over 26 to 2/13, and that's the coordinates of the hole right there. That's where there'll be a gap. All right. So horizontal asymptotes, consult Bobo Botten, and you'll see that it is bigger on the bottom again, so it's 0 it approaches. If this had been x to the third, it would have had a horizontal asymptote of 1. And if that had been x to the fourth or bigger, it would have had no asymptotes. The vertical asymptotes, if any, there are no vertical asymptotes. Did I write that down? No vertical asymptotes. The exact coordinates of any holes, I did that, found that. The domain, it's all real numbers except for that hole, so it can't be equal to 5. And the range is going to be all the numbers that are trapped in this zone right here. So I just did a trace, and I found that the lowest value down here was negative 1.2 approximately. The highest value it'll ever be is about positive 2.07, and I can just write that out in English language, or I can put it in mathematical notation here. This is a little bit harder than you probably find in the real test. Your intercepts for x and y are simply over 1 and 0, and down 1, so 0, negative 1. I find those by plugging in 0 for x, and then solving this for when this equals 0 and cross-multiplying and solving. Okay, we're in the home stretch here. The owner of an SAT tutoring business with 1,000 happy customers brags that not a single client has ever scored less than this value. And here's the data to prove it. They randomly sampled 13 former customers, and guess what? None of them were below that. However, you're smart. You realize that they're approximately normally distributed, and if I do a standard deviation, I can use my good skills with the normal curve to estimate that by finding the standard deviation and doing a normal CDF, with 475 as my boundary, my mean value of 617, and knowing that I've just found the standard deviation of 74, that in fact about 2.8% of all of those 1,000 customers, or about 28 customers, I would estimate, would be below 475. So I would argue that it is not possible that they had no scores below 450. Okay. The z-score for this highest score, the z-score for 775, when you know your mean and you know your standard deviation, there's a little formula for that. It's just figure out how far separated you are, the high score minus the average score, and then divided by the standard deviation. And that's going to tell you your z-score. There's your z-score. Okay. If you think some were below 475, estimate how many, and I did that with 28. Okay, we're on to the last one here. Solve completely and clearly for all possible triangles. We have an angle and two sides. Unfortunately, when you see angle A and side A repeat, this is the ambiguous case. The ambiguous case is tricky in that we want to draw it carefully, draw the unknown side across the bottom. So if we know A and B, this is C. Or B is 12 right here, and this is the side that's hinging, that's 15. Luckily for us in this problem, 15 is longer than 12, so there's no way that that gap is going to be anything that's longer than 12. So as this comes around, it's definitely going to hit, and then it's longer than 12, so it's only going to hit once. So we have just one possible triangle. I'm going to solve it by using the law of sines first. When I do that, I get angle B is 25.6 or 52.6. I use the triangle sum to find the other angle, and that's 44.4 degrees. And then I use the law of sines again to solve for the missing side, and that's 10.57. And I am done.